We are live.
We are live, so we can start, right? So hello everyone after the lunch break. I'm Mateusz Motyliński. I will be chairing this session, and this session will be about scientific character than the technical one, as we had before lunch break. And the first speaker is Tanja Petrushevska from University of Nova Gorica. Tanja will tell us about nuclear transient, specific nuclear transient, PS16 EPN. So Tanja, you have 25 minutes plus discussion. So you can start your talk. Thank you.
Thank you, Pavel. Thank you, Łukasz and the organizers for this great opportunity. And those that are here or on Zoom digesting the
That's the microphone.
Okay. So again, thank you for this great opportunity. I would like to say a few words about this Ivan Strong nuclear transient case. And this is actually recent work that we have submitted to ANA. And perhaps many of you have already familiar with my institute because we have also organized one Gaia transient workshop in 2018. But for those that don't know me, I'm working at the Center for Astrophysics and Cosmology in University of Nova Gorica, which is close to the Italian border.
Too many times.
Okay, so for those that are not strictly familiar and not working in this field, let me just say a few words of introduction about tidal disruption events. So what are these? So today we think that in the center of all galaxies, there is a supermassive black hole lurking there. And if by any chance there is some kind of a star that is being quite close, that is getting very close to the black hole, then it can happen that the tidal forces of this black hole actually get so strong that are stronger than the binding gravity of the star. So what happens is that star gets disrupted by the black hole. And this classical picture, this idea was actually put forward by several theorists since the 70s, where the star gets disrupted, and then half of the debris of the star actually remains gravitationally bound in a range of eccentric elliptical orbits. And then an accretion disk is formed, and the heat is actually transformed into radiation, which we expect that it should peak in the X-ray domain. And continuing on this, let's say, canonical picture that we have that was put forward of TDs, then if we consider vanilla Schwarzschild black hole, then we expect to have a tidal disruption event happening only in close to supermassive black holes with relatively low mass. So let's say less than 10 to the 8 solar masses. And this is because we need to have the tidal radius outside the Schwarzschild radius, because otherwise the tidal disruption, the whole star just gets swallowed, so we don't get any of the luminous flare that we would expect to get in this tidal disruption event. And there's several consequences. One expects that the TD luminosity, the TD light curve, should follow the fallback rate in sense of some kind of a power law decay and the form of power law minus 5/3. And so this fallback rate and let's say the light curve depend on, among other things, they depend also on the properties of the sort of like the mass of the supermassive black hole. So that's why everyone got so excited, because observing TDs in quiescent galaxies then can provide a way to study supermassive black holes, because otherwise they are not we are not able to probe. And this is especially interesting in galaxies outside our nearby universe, where these things are very poorly constrained. And the situation that we have today is we have at least 60 or more tidal disruption events. And as you can see on the left side of the slide, and most of these are actually discovered by optical surveys. So like Gaia, but not only, ZTF we heard of, IPTF, and Assassin, and many other surveys. And actually that canonical picture that I showed you before is not really what we are seeing today, because most of these tidal disruption events are peaking in the UV or optical. And why is this the case is still a very lively debate. However, once going forward, looking at the Vera Rubin Observatory, which will start to function in a few years, we will expect to have few of these tidal disruption events each night, so potentially being discovered on a nightly basis. And however, at this moment, we only have a few TD candidates, which are not in quiescent galaxies, but they are in galaxies with active galactic nucleus. And this is partly because in these optical surveys, many of the times transients that were found in the nucleus of a known AGN they were actually excluded for being followed up with observations, because we know that AGN can be variable sources. But there is no one single physical process that actually tells us that TDs shouldn't happen in galaxies with AGN. In fact, there are some works that even suggest that TDs in AGN can even be more efficient in creating the accretion disk, because there is already a pre-existing disk. And recently, people have been paying more attention to transients, and they've been discovering and reporting transient in AGNs. And I think we will also hear we will hear more about this from Nada and Mariusz in the next talks. But at this moment, once we have a luminous transient arising in a AGN, in the nucleus of an AGN, then we don't have like one smoking gun signature that tells us exactly what is this, or what is the physical mechanism behind this luminous flare. So of course, it can be a tidal disruption event, but we also have this so-called changing look AGN, which is basically the definition of some kind of a dramatic, so extreme change in the photometric and or spectroscopic AGN properties. And what is exactly causing this dramatic change is a matter of debate. It can be some change in the accretion rate, but what is causing this change in the accretion rate is still being lightly debated. There are even some suggestions that some of these can be caused by supernovae happening close to this nuclear region, or it's also possible to have microlensing in the line of sight, which of course is extrinsic. and other things which I am not putting in this bullet point. However, we're still at this point. We're still at the time that we need to look at this case by case to see what, and studying them with more data as possible to look what is happening here. So I will now focus on this one case study that we have done, and this is PS60 DTM, and this is a transient which was discovered in 2016, as the name says. And the first data points, photometric and spectroscopic data, actually was reported that this, given the implied magnitude, this is some kind of a superluminous supernova. However, then a study that gathered 200 days of observations actually concluded that this is consistent with a tidal disruption happening in a host galaxy with an AGN, with more in particular narrow line Seyfert-1 galaxy with a low mass supermassive black hole. And this, if we take a look at the light curve, the transient rose relatively quickly over, let's say, 2 magnitudes over the host archival data, and then it stayed on some kind of a plateau for 100 days. And okay, now this, I want to go to the next one. Okay, and another very interesting peculiar property of this transient is that once PSDTM outbursts happen, then the X-rays that were present there in the archival data, they were, let's say, depleted. At least an order of the magnitude, they went below. And so the authors of this first work suggested that perhaps some kind of a disk was formed because of the tidal disruption, and this disk is actually blocking the X-ray emission in our line of sight. And they also predicted that these X-rays should come back once the accretion rate of this event start to decrease. So now I will focus on our study, which is basically 6 years of monitoring this this TD candidate. So here I'm showing you the photometric data we obtained with so from near UV to optical. I'm showing here over let's say almost 6 years, and now we are seeing that it's going back to its pre-outburst levels. And interestingly, if we, especially the near UV data, is showing that the decay in the first more or less 200 days is quite similar to what one can expect for tidal disruption events. So this, let's say, time to -5/3. But then afterwards, the decay becomes much slower. And there are some works already showing that this has been seen in other tidal disruption events. So some have put the hypothesis that perhaps there are 2 different mechanisms behind this light curve behavior. And now let me show you the mid-infrared light curve with Ys, near Ys. And the mid-infrared response for this PS60 DTM is actually quite amazing. And here I'm showing in the plot, I'm showing the Atlas data, which we have very nice data because it's we have pre-outburst data as well as quite nice data points on the let's say rise on the rise time. And we can see that the mid-infrared and the optical are almost, they're detected almost on the same time. And it is interesting that there are already TDs in the literature with detected mid-infrared flares. And these, let's say at least 11 of them. And these have some kind of a time delay between the mid-infrared and the optical. And as it's very custom in Asian research, the time delay between the mid-infrared and the optical can be interpreted as the time for light that it takes to travel to the dust-emitting region. So yeah, in the literature, these things have been interpreted as dust echoes. But here, of course, we have in the beginning of the data, there might be that either the optical or the mid-infrared started first or the other, even though the optical have quite a good coverage. Then we have the mid-infrared, which at the time of speaking is still rising. You can see that even after 1500, 1700 days, it's still rising. So that's quite an amazing behavior. There's also another way that we can try to estimate what is the distance to the dusty torus, and which is usually done also in Asian research. And one can estimate what is the sublimation radius of the AGN. And of course, this depends on the bolometric luminosity, as well as other properties such as some assumption about what kind of dust is it, what is the sublimation temperature, and so on. So for the PS16DTM host, we can estimate this value before and after the outburst, and we can get something like 20 light days and there's 150 light days after around peak. So in these, if we expect that the mid-infrared light curve should peak with a time delay similar to the time that it takes to the dusty torus, then really we are not seeing this in the observations. So now let me show you the spectra that we have gotten of this transient in this time frame of several years, because they are depending on what is your research field, but there are not so many in our research field. There are not so many transients that are followed with such a long time baseline. And so of course, the most striking features that we are seeing over time over time is that the continuum, the blue continuum, drops over time, and then we're seeing strong hydrogen Balmer lines, and these also vary with time, and we can also distinguish three different components. So perhaps the most striking features that we're seeing in this transient, in this TD candidate, is the iron emissions. And here are highlighted in the plot with this pink bands. So we are seeing very strong iron 2 emission complexes, broad complexes. I will say a few more words about this. And I'd like to stress that this broad iron 2 emission is actually transient, so was not present in the archival pre-outburst spectrum. And in our last X-shooter spectrum, actually it disappeared almost completely. And for those that perhaps are working with AGN, especially with narrow line C31 galaxies, you will say, okay, well, we have these are not new because the iron lines are very common in narrow line C31 galaxies, but they have never been detected so strong as in this case. And of course, the question, where are these iron, where does this iron emission is coming from is the question we can all ask ourselves. And there are some works that are suggesting that perhaps iron emission comes from the sublimation of ice grains that are in the inner torus. And these are, so we're seeing an iron emission from the sublimation of the dust just because we have the increase of emission from this tidal disruption event. So this was triggered by this tidal disruption. So we got intrigued by this, and we have looked at nuclear transient where the iron emission was reported, was claimed, and so we looked at what is the how does the mid-infrared light curve looks like, whether they have mid-infrared emission or not. And here I'm only showing those that are classified as tidal disruption events. So here I'm showing those events that are in the literature with claim iron emission. And you can see the first spectrum that is plotted there is our PA16TM, where you can say that it's obvious that the iron emission is very strong. And on the right, we can look at the mid-infrared light curves from WISE, and we are seeing that at least two of these have a strong mid-infrared response. Though let's say they have some kind of a completed evolution, since they have a rise time and a decline, while our PS16TM is still rising on this time scale. And the one that doesn't really have a obvious mid-infrared emission is actually that with not so strong, maybe even dubious iron emission. So it is possible that there is a connection between the iron emission and the mid-infrared emission. So we wanted to study, given this transient iron emission, broad transient emission, we wanted to study what is the temporal evolution over the years. So to do that, we had to develop a model for this. So we made the semi-empirical model where we were able to study, to identify and study the evolution of the emission lines. This code is called Fantasy, and originally was developed for fitting AGN spectra. It's also publicly available, so you can take a look. Importantly, the code was able to identify and reproduce all the spectra, but only in the case when the broad iron 2 emission was present, on top of which we also had a narrow iron lines. And if we look at this so-called light curve, so the temporal evolution of the flux in these lines, of this broad iron lines, we do have some gaps in the data, but one can say that around 400 or maybe even before, there was some kind of a peak. So we have some rise and then some kind of and then a decline. So then if we compare this these times on which we have the variation of the mid-infrared light curve, the optical and the iron, the broad iron 2 lines, then we will see that these three, they all evolve on different times. So we cannot say that if the mid-infrared and the iron 2 were evolving on, were reaching the peak on same time, we could have said that there is some kind of a one-to-one link, but so far this for this transit was not possible. And of course, we looked at X-ray data because this is intriguing, as I said in the beginning. We looked at the Swift X-rays and the Chandra, which has taken data in these years. And at this time, even after 6 years, despite that the optical, as I said, has gone back to its pre-outburst levels, we are still seeing the X-ray emission being suppressed. And this is very intriguing also because in our last X-shooter spectrum that we obtained at after 1900 days past outburst, we are also detecting at least one weak coronal line, which will require some kind of a weak X-ray source, some soft X-ray source, which we are not seeing. And you know, detecting coronal lines at late times from TDs is not the first time. Actually, this year we had reports, at least 2 works where coronal lines were detected in a TD at 1700 days. This is the work from Francesca Lonori. But in that case, and the other case as well from the literature, we had the rebrightening. It was also followed up by a rebrightening, and simultaneously there was also rebrightening in the X-ray emission. So as well, this is a puzzle. So with this, I would like to conclude. So perhaps by doing this work, we have opened ourselves even more questions than answering. Yeah, I showed you here the work that we have submitted with my colleagues Lelo Gudas and Ilic. I showed you here nuclear transient TD candidate in a narrow line Seifert, so Asian host. And this kind of work is important before we get all those different types of nuclear transits that we will not be able to distinguish in the Rubin Observatory. I've shown you a relatively short rise near UV optical light curve, but then long-lived within like 6 years of photometry, and extraordinary transient iron, broad iron emission, which disappears, and then a very strong mid-infrared response. And I still don't have the answer where these things are coming from. We try to answer by looking at the dust stories close to the black hole, but this the timescales cannot be are not so simple here. And we also see at least one coronal line, but then the X-ray is still being suppressed for some reason. So then it's difficult to explain, especially because the optical data has returned to its pre-outburst levels. And we can even ask ourselves if we look at the data for those AGN, extreme AGN variations, the so-called changing look AGN. So perhaps some of those that show a dramatic increase in the photometry and in the spectra, perhaps some of those are triggered by a target deception event that is making some kind of a change in the accretion state. And with this, I would like to finish, and thank you very much.
Thank you very much, Tanja. It was a very nice introduction. At first, maybe one comment to Zoom participants. Certainly, please do not hesitate to ask questions on Zoom chat or in Slack channel. But let's start with the question from the audience here in lecture room. Przemek?
Thank you, Tanja, for the wonderful talk. I'm not sure. I was outside for a second. Maybe I missed it. But did you make any polarimetric observations, maybe to determine the grain size?
No, it's not. I think my collaborator Yorgos Leloudas is getting into this polarimetry and TDs. So I think it's a new thing, new hot thing. But I think it has to be very bright to do polarimetry, right? It has to be, I think those works that have done some polarimetry of TDs, they are like the very nearby thing. So I think it has to be very bright.
Well, it depends on the precision you want to get for these measurements. Because photopolarimetry is possible for really faint, like 17, 18 Mach star. But you know, it's a question of precision you want to get.
I think this one was already like 18 magnitude or so. But, yeah, definitely polarimetry for TDs is it's a very new and interesting field.
More questions from the audience? Do we have some in Zoom? Yes.
Nothing on Zoom. So this was fairly bright TD, I guess. They're quite rare, I think. So because this looks like this was, 2,000 days of observations. That looks like a perfect science case to add to our BH-TOM. So that's a kind of a comment to urge you to think of next TDE and to add it to BH-TOM and then see what happens, because there is, multi-wavelength observations, multi-epoch spectroscopy as well. We have all the capabilities, and we haven't done this yet with TDE.
Yeah, absolutely. I was thinking about that when you were presenting the BH-TOM. Exactly.
One more question, Mariusz?
Just have the comments. We don't have any TDE.
Microphone.
The microphone, please.
We don't have any TDE because you prioritize microlensing.
Well, it's up to you. You should add it.
Yeah, and then we also had there is even data that I didn't show that plot because we had Atlas data and other data that was already good enough. So perhaps getting even more that kind of stuff.
Okay, so thank you, Tanja, again. Very nice. Let's move on. The next speaker is Mariusz Gromadzki from Warsaw University, and he will be talking about Gaia supernovae and other extragalactic transients. Mariusz, you have 15 minutes plus questions.
Hello. So I have the big luck to be the optical postdoc, and I work on this wonderful topic, time domain astronomy. For me, the time domain astronomy are transients. So as you see, I'm involved in many collaboration. Most of them are spectroscopic classification and follow-up of the transient, different type. So I also use my skills in the spectroscopy to the spectroscopy of microlensing. But today I will talk about the. I make some kind short biased review about the transient, extragalactic transient discovered by Gaia. So Gaia was designed as a astrometric mission, but we see, and thanks to Łukasz, it's done for the wonderful transient facility. And you see there are lots of advantages. It's the old sky, the magnitude range is very deep, it's 21. It's the one of the deepest transient survey now. So it's the weather independent and give also the additional information like the very precise position and some colors using the PPRP low resolution spectroscopy. It also has some disadvantages, which is the problem of cadence, which is typically 1 month, and of course there is some delay between discovery and reports of the transient because it's the satellites work far away and we cannot transmit the data constantly. We just download the data from time to time and then we can process them. Okay, I say that this is one of the top survey facility, and according to the transient name server, this is the third most productive transient facility. The first one, of course, is the ZTF. The second one is the Pan-STARRS, and the Gaia take the third place. In the transient name server from 2016, there was registered over 100,000 of transients, and Gaia report over 16,000 transients, and this is the third place. Of course, because of the 1 month cadence, the typical supernovae discovered, this is the random one selected today from the all reported by Gaia alerts. It just looks like that, like 4 points, not much, and this looks like that. This is 1A. The classification was reported by Nat's team, by Morgan Fraser. Okay, this is the other case. It's just 1 point, but this point is very important. Okay, and we see the follow-up observation. And you see at the beginning of the light curve 1 point. This is this 1 point I showed before. And this target is very interesting. So it just looks like the host identification is very difficult because it's between of the group of the some galaxies. And we have the other photometric follow-up, and we have some kind of the Gaia points, but this is not real Gaia point. This is the synthetic Gaia magnitudes estimates based on the spectroscopy. And this work was led by Isaiah Dong and from California, University of California, Davis, and he finds that this peculiar object quite fast evolving. You see that the day phase just covered the 60 days. It's turned to the untypical 1A supernovae, and ignition was happened in the thin layer of the helium. Okay, this is the other interesting transient from Gaia, and in this case you take a lot of points and you see that the light curve is very untypical. You can say that it looks like the weird microlensing stuff, but this is quite a nearby galaxy, and this is embedded into this nearby galaxy. And this paper is led by Sean Brennan from Dublin College, and he published 2 papers. One paper is very extensive description of the spectral evolution, photometric evolution, and the other papers is set analysis, and based on this set analysis in the case of the progenitor of the events. And in case of these events, we are not sure about the nature. Is it the supernovae or is it the imposter? Okay. And this is my favorite transient among all I represent today. And it has not much common with Gaia, just one detection. Here, this is the tidal disruption events. This event was classified by me and Nada Ihanec, and then Thomas Wavers was in our support during our run. And we immediately discovered that this is the TDE. It was published. I'm the first author of the Astronaut, so this is my discovery. So, but the paper was led by Thomas later, and we take a lot of data, including the full photometry by Las Cumbres Observatory facility 1-meter telescopes. Then we use the Swift telescope. We also got a lot of spectra using the NTT. We got the spectra using X-shooter, and on these plots you have the line profiles taken by X-shooter, and you see left side you see helium-2, and the right side you see H-alpha. And what Thomas find, he find that in this case we have elliptical disk caused by the derpis of the material taken from the star by black. Okay, this is the object of Nada Ihanec, and she will after me talk about this object, and I will not say much about that, but this object is very similar to the object presented by Tanja, and we also see the very strong iron lines, and I will not say more, Nada say much more than me. Okay, at the end, this is my private object. In this case, the object was discovered by Ogel survey, and we take the extensive spectroscopic and photometric follow-up using the various facilities. And in this case, we have the we see nice spectral evolution sequence. And unfortunately, in this okay, in this moment we have the seasonal gap. And these green points in seasonal gap was points taken by Gaia. So Gaia is not only the discovery tools, it's also the tools which facility which derive the very crucial points. So, and this is everything what I would say. Thanks.
Very much, Mariusz. Perfect timing. There is a lot of time for questions, so let's start with the lecture room. Maya, please.
Hello. Could you please show the slide with this event that had swan detection? And did I understand it correctly that it was TD? I forgot the name. I'm sorry.
I can back.
Sorry.
Put you back to the ZSO. One more. Okay.
Oh, yes, this one.
Yeah, this is the tidal disruption event.
Okay, so this detection line, is this fall off so quick? Because I'm not an expert in TDs, but this is unlike any TD I have seen. So I'm curious.
So this is the huge variety of the events. As Tanja showed you have the different host and you have the different time of falling. So it's very dependent on the start, which is disturbance, of course, of the mass of the black hole, and environment also is important in this case.
But the detection, then after detection, then the next point is like after a year or half a year. So there are TDs that last 3 months only.
Yeah, 3 months is a typical time scale for the falling.
Okay. Thank you.
So maybe I have a question about this target. What was the criterion that you selected this target as a TDE?
Okay, as a TDE, I don't show the spectrum, but the spectrum is very blue and it shows the very broad helium-2 lines, and this is the way how looks the tidal disruption events at the beginning of the.
So after having this Gaia light curve, you get some spectrum.
Yes.
And check the
spectrum.
The spectrum. Okay.
5 minutes after observation.
5 minutes.
Yeah, more or less.
Okay, nice. Okay. One question more.
Well, you showed the Ogle event, the Ogle 17J, and which was found by Gaia, which I didn't know. But could you say a few words? What is it? Do you have any idea?
Yeah, we have an idea. This is like type 2n supernovae. So in the moment of it starts increasing more or less like the normal type 2 supernovae, and and we take the spectrum more or less in this time, and it shows like the young supernovae. But we have like 20 days, and it shows features like the young supernovae, which is very blue and very narrow hydrogen lines, plus the helium and nitrogen 3 quite broader line. And after this moment, it has around 17 absolute magnitudes, and then it goes over 2 magnitudes higher. It is like almost 22, very bright, and you see how it's fall. It's fall like shows lots of variation, which is not typical observed in the supernovae. This is the effect of interaction with the circumstellar matters, which is lost before explosion, and then we have the sudden decrease. And these additional points from the Gaia could allow us about the rate of this sudden decrease. And after seasonal gap, there was no detection. It's completely fade.
Cool.
We have one question on chat, right?
Hello, am I audible?
Yes.
Yeah.
Hello. Yes. So in the same slide, Mariusz, is it a type 2n you are saying? I did not understand, or is it an interactions of the TD material with the surroundings?
The last one is definitely type 2.
Type 2. Okay.
And you see broad H alpha, and then you see the rest of the spectrum is like the type 2.
Yeah. Okay. So yeah. Okay. Thank you.
Thank you, Rupak. More questions on Zoom? No questions on Zoom. And I don't see any questions, any hands here. So thank you, Mariusz, again.
Thank you very much.
And now if we have Nada Ihanec on Zoom, I hope she is here. She is with us. Nada.
Hi.
Yes, you are.
Hi. Yes, yes.
Very
I just
good.
need to share.
Nice to hear you. Yeah. So it's time for a presentation made by Nada Ihanec remotely from Warsaw University. But Nada is currently at ESO scholarship in Chile. So it will be about the mystery of high amplitude AGN activity. Nada, please start.
Yes, thank you. So yeah, like Pavel said, I will be talking about the mystery of this high amplitude AGN variability and activity. So I must say first that it's still unknown, and this is still it's still in the study. So first, why am I interested, or why do we want to study the AGN variability and the variability of the centers of galaxies? There are two main reasons which are more or less connected. So the main one is that we want to study black holes in distant galaxies and the environments where the black holes are. So up until last year, the only black hole that we were able to measure and to study directly, or not really directly, was the galaxy in our own, the black hole in our own galaxy. And this was measured, the mass of it was measured with the position and the movement of the stars around it. And as you all know, the Event Horizon Telescope was able to get the first image of the black hole first in M87 and then also in Sagittarius A. And this we were able to measure and to study directly the environments of the black holes. However, this has only been done in M87 and in ours, and there are so many more galaxies in which we know that there are black holes, it's just impossible to study them. So for the active galaxies, which do have the black holes inside as well, and we have this accretion material on the black holes, this is one of the ways to study them. In connection to this, the other problem occurs, which is on the right side, you have this for long believed unified model of AGNs, which basically states that there are different types of AGNs, and depending on the inclination of the host galaxy, so depending on which area of the AGN we see, we have different types. However, with the discovery of changing Luke quasars, this theory kind of became almost impossible, because in changing Luke AGNs, we have, for example, changes between Seyfert 1 galaxies, which are the broad line galaxies. So we see the broad spectral lines. And those lines in the span of few months, they change to the narrow lines. So that would mean, which are the Seyfert 2 galaxies. So that would mean that the inclination of the galaxy changed in 6 months, which is impossible. So the reasonings behind the idea and mechanisms behind all of this is now a great way to study. However, then of course occurs the complications with nuclear flares. So the main one is the actual definition, or what is the nucleus of the galaxies. So the problem is that in the galaxies that are near to us, to fairly close ones, as an example of the one here on the top, we are able to say with quite certainty if an event happens in the nucleus based on the localization of the event, which is here the pink cross, and then the location of the pre-location of the galaxy. So in the case of Gaia 19 EKS, we were able to say with fairly certainty that this flare happened in the nucleus, and in the end, we were right. However, in the case of, for example, in the bottom one with Gaia 19 DHD, so this galaxy is so distant that even though Gaia has a really great precision, we are not able to say with certainty if this event happened in the nucleus or just close to the nucleus or somewhere else, depending on the view of the galaxy. And the reason why, like I said, we want to study the nuclear flares is so that they are connected with the black hole, so that we are able to study and derive the properties of the black hole. And the nuclear events, so all the events that are connected with the black holes are the changing blue quasars, which I mentioned before, tidal disruption events, bone fluorescence flares, and some maybe unknown phenomena. We had a really nice introduction also on tidal disruption events from Tanja, but just to recap, so the tidal disruption event occurs when star comes too close to the central black hole in the galaxy, and the tidal forces of the supermassive black hole disrupt partially or totally the star, and this produces this really luminous flare that is visible in great distances. So the mass of the black hole for which these events would occur are between 10 to the 6 and 10 to the 8 solar masses. And some of the observational features, what Mariusz mentioned before, the way that we classify them is that they show they're really luminous, really hot, and they have really blue continuum in spectra and show broad helium-2 lines and or broad Barman lines. They're really heterogeneous group, but so it's really important to get as many information and as many targets as possible. And they can occur both in quiescent galaxies and in AGNs. The next type are bone fluorescent flares. So they've been recently discovered. So there are flares in the center, of course, of active galaxies and also maybe quiescence. So the main drive is the bone fluorescence. So what happens is that we get increased UV optical emission, and this triggers photons from Lyman alpha-like transitions of helium-2 at the around 300 angstrom. And this excites certain stages of oxygen-3 and nitrogen-3 due to the wavelength proximity. This creates the cascade of transitions, which is visible in the strong emission lines of helium-2, nitrogen-3, and oxygen-3. And the interesting thing about this bone fluorescence was that it's been well established in planetary nebula and X-ray binaries. However, it's really rarely seen in AGNs. So yes, those are few of the types that we know so far that drive the flares from the nucleuses. So how can Gaia alerts help? So as it was said today, that until yesterday, Gaia published 21,455 alerts. And out of those, 160 were pre-classified AGNs, and then around 100 BLAC, 1,000 quasars, and a lot of them are not pre-classified, so they're unknown. And all of these together, if you check the localization, around 10% are nuclear alerts. And since 2019, there was higher increase in detection of these nuclear events, especially the slowly rising one due to the new filters. And all of these nuclear flares have really variety of light curves. So 3 examples are shown in the bottom. The first one that I started working on, and I did the most study out of all of the examples I will show, is Gaia 19 AXP. So Gaia 19 AXP was alerted in March 2019. So the red line here shows the time of the detection, time of the alert. In overall, it exhibits almost 2 magnitude flare. It lasted for 2 years. And before that, the galaxy, so the host showed some small prior variability, which is seen in Gaia data. However, the Catalina survey also observed this galaxy, the host, from 2005 to 2013. And as you can see, there's no pre-flaring. We have the SDSS also observed this in 2005. and it was classified as narrow line cipher 1 galaxy. So this was the first flare, bone fluorescence flare, that was found in the pre-classified active galaxy. We got 2 years of really well covered in different wavelengths, the photometry and spectroscopy. So I just wanted to show the full light curve evolution. And on the right side, you can see that the neovice also observed this event, and you see the delay, as Tanja also mentioned before in some of the cases. So there is delay in the near infrared evolution based on the optical one. So optical is already, so it's back to the baseline, while in infrared it's still flaring. And this kind of created the drive for me to study and see what else we can, what are other events. Oh, sorry. First, the spectral evolution. Yeah, again, one of the reasons for this classification was this bone fluorescence, so strong oxygen 3-lined, nitrogen 3, and helium 2. And in this spectral evolution on the right, the interesting part was that we noticed that during on the rise and during the peak and the decline, the bone fluorescence was fairly strong, and then the target went behind the sun, and we see the decrease of boron lines, so of decrease of nitrogen and helium, and we see increase in iron, which was really interesting. And this happened more or less at the same time as we see huge decrease in UV from detection from SWIFT. So this can kind of prove that the boron fluorescence is in fact driven by UV emission. And what I found interesting also in this event is that in the archival spectra, so as you can see here, the black one in SDSS, the iron is present. However, during the decline, around 260 days after the peak, we see much stronger increase of iron than it was in the archival spectrum. So yeah, this kind of drew my study of the other amplitude, high amplitude flares in Gaia. So my criteria to find them was that they all had to be so the location of the flare has to be in the nucleus of the galaxy, or at least what I believed was the nucleus. I focused on small or non-prior pre-flare variability. And the reason why I also focused on no prior variability is because some of the host galaxies, they haven't been classified yet. So we don't know for sure if they're AGNs or not. They should have non-repeating flares, especially these high ones. And I believe I never actually saw really high repeating flares in any case. And all of the flares have to be higher than 0.5 magnitude. Overall, this gave me, so I got time on INT, and I obtained spectra of 34 targets. This was during 2021 and in February and April this year. And in addition to this, I grabbed also the data from other instruments, so Catalina, Pan-STARRS, ZTF. And I will show you some examples. So the first one is Gaia 19 BZP. And this work, I must say from the start that it's still ongoing and it's preliminary. So the spectra, I don't have that many spectra, but still. So the Gaia 19 BZP was alerted on 13th of May, 2019, as you can on this point. And the last pre-detection was 39 days before. So it was really fast and high amplification. We obtained spectra in February 2022, which is around here. I hope you can see the position of my mouse. So at around the peak of the last bump. So the spectrum showed that this galaxy, so the redshift of 0.15 and the peak magnitude of the magnitude of the first peak, the absolute magnitude is -23. So we got spectra for this on INT and on the Himalayan Chandra telescope So the spectrum here is from the June 2022. So, and if you zoom in, it's slightly better resolution, but in the February spectra from INT, we see that there is a hint of nitrogen-3 and helium-2, which which are indicators for boron fluorescence flares. And as this is extremely long transient and it's still ongoing, so there is a chance that this was actually driven by boron fluorescence. Then the next one is Gaia 19 BBW. So this one was pre-classified as BL-LAC, though I'm not really sure based on what they classified this. So on the right side, you see the light curve. On the black points are the Catalina data, where you see some prior variability, 0.5 more or less magnitude. But then with Gaia, you see all of a sudden this almost 2 magnitude increase. On the left is the archival spectrum from SDSS. And it was, I think they're doing automatic classification, which in this case is, I believe, wrong, because this one, as they classified it as Lyman alpha line at redshift 5.9, this is not the case, and also our spectra show this. So these are in reality the H alpha and oxygen 3 and then H beta at the redshift of 0.29. The next one is Gaia 21 FNN. So this was the similar case of the wrongfully determination of the redshift. So originally it was 6.16, when in fact it turned out that again, this is the H alpha, oxygen 3 and H beta at the redshift of 0.33. And you see that there's a really almost non-variability in Catalina. And then you see this high increase in optical in Gaia and ZTF. The next one is Gaia 21 CLO. So it was detected or flared by Gaia in May last year, so around here. And here in Catalina, you see some higher variability than in cases before. Well, it's still 0.2, but we have almost 0.6 flare and it's still ongoing with the archival spectrum on the left. So the ciphered galaxy. 4 more examples of the targets and events that I've studied. So in case of, you see all of them have some variability or really small variability in Catalina data. So I must say in the case of Gaia 21 MCY, this is really faint object and also faint in Catalina. So this is quite noisy, and but still you see almost non-variability. So in the case of the top left, EXS, so this one, it's been going on since October last year. So it's still ongoing and it's a fairly long flare. In the case of Gaia 21 FCA, the whole flare, so from the start to the end, it was in the span of 18 months. In the case of Gaia 21 CMY, so the flare started in November 2022, and it still haven't come to the baseline. And then we have the case of Gaia 21 ETX, which it started flaring in July last year, and it's still ongoing. So all of them, the spectra were obtained in February or April this year. And then there are 2 special events in all of those 34 that I've studied. So these 2 show the problem and issue that I mentioned in the beginning about the localization and definition of the nucleus. So optically, visually, both of them look like that they occurred in the nucleus of the galaxy. However, Gaia 21 FCD, the spectra showed that this is supernova type 2 at the redshift of 0.018. And in the case of Gaia 21 FAM, the flare, so this point occurred in October last year, and the obtained spectra in February, so 4 months later, already showed just the galaxy spectrum, or because it was I observed with it INT, and at the magnitude of 20.5, it was just noise. And then in May this year, the next Gaia detection occurred, so we know that it's back to baseline. So yeah, for sure, this was probably a type of supernova as well, just that occurred just super close to the nucleus. And with this, I will finish with conclusions. So in the last few years with Gaia and all of the other surveys, we start to see really big diversity of nuclear transients, both in optical and spectroscopic evolution. And we know that in the future, with all of the LSST and other telescopes and instruments, we will see more of them. We discovered really peculiar object like Gaia 16AX, PS16 DTM that Tanja was talking about. And really, it's challenging to find the models and mechanisms behind the changes. So it's important to study them and try to get as much information as possible. And I think, well, at least I'm really looking forward to see these new transients and to finish the currently ongoing study. So that's it. Thank you.
Thank you very much, Nada. Very nice talk. So, do we have questions? Mariusz?
Okay, Nada, very nice talk. I have the question. In case of this ongoing Gaia transient, do you get spectroscopy because it's not clear?
Yeah, so all of the ones that I mentioned, I have spectra. The brighter ones have better resolution, so it's easier to study them. But I didn't show a lot of them because I'm still working on the reduction and also especially the flux calibration. So, but we know for sure that like the lines which are there. So you're asking about this one, BZP?
Yeah, it's about this crazy one.
Yes, yes.
Could you say what they shows in the spectra?
So it shows for the continuum. So the problem in we have the from the Himalayan Chandra telescope, the continuum is more or less flat. But the problem here, I cut at the bluest part because it's really noisy. So below 4,000, we don't really see any lines. And then in the case on the INT spectrum, which has better resolution because it was observed at better conditions, it does show a slight increase in the so the blue continuum.
So I'm especially interested about this target you showed just SDSS spectra.
So
I mean, this very broad, with very broad H alpha and H beta.
Yeah. For this, I was able to determine the redshifts from the H alpha and H beta. So, and it is different than this. So I just, because I don't have the properly calibrated spectra, I didn't want to, show it here. And
they just show the divergence?
Yes. Yeah.
Thanks. Another question from Tanja.
Another great talk. I wanted to ask you, so you only looked at Gaia data to find your candidates, or you also looked in other?
No,
or you used ZTF just once you had your target, and you dig up other surveys. You dig up
My initial sorry. No, yes, my initial study. So to choose the targets, I only used Gaia data, and then the good thing about all of them, I think only one of them doesn't have ZTF data, but all of them are northern targets because I observed them with INT. So it's good that ZTF has a nice additional data. But yeah, I only focused on the ones discovered by
And you don't
Gaia.
know what is going on, these bumps, what are these bumps, I guess.
Yeah, yeah.
I wanted to ask, did you also look at neowise, what is happening with the mid-infrared?
Yeah, so this is one of the things that I will still do. So I will grab, I'm planning to grab also the neowise data for the ones that were observed, and any additional Galax archival one to see what's happening. So, but I haven't done that yet, but I'm planning to.
Great, looking forward.
Yeah.
One question from Łukasz, right?
Nice stuff, Nada. I'm just wondering, looking at this one, so the SDSS spectrum is probably all over internet, right? Because these archives, they've been copied, so probably NED has them, right? So what do we do? How do we correct them? We should make sure, you know, the correct ones get. I'm sure you add those spectra to TNS, right? That's what you do, I hope. Yeah. But how do we fix NED? Do they realize that they got the data wrong?
So actually, in this case, I believe in case of BBW, this one on NED already has the correct redshift. I'm not really sure where they got it from, because it was really interesting for me to see, because as you can see, SDSS does say that it's 5.9. Well, in the case of, or I think, so now I'm really not sure, either in this case or in the previous one of them, I know that on NED, it does have the correct redshift, but I'm not really sure how to fix it on NEDs, because I haven't uploaded them to the TNS, and I am planning to. So TNS will automatically have the correct redshift, which maybe NED will then take it. I'm not really sure, but yeah, it's for sure one of the things that it's good to check.
Question from Rupak, please.
Hi, Nada. Nice talk. So do you think that these are all TD-like candidate, or do you also think that there may be other possibility of possible transients?
So yeah, one of the reasons why I was focusing on more than 0.5 magnitude flares was I was hoping that they would be either TDs or Bowen fluorescence flares, or something in this case. Quite a lot of them show that they're just changing AGN, so there's just changes in the lines, and I'm not really sure what this could be, and how this can happen with such a 2 magnitude optical increase. But yeah, I started looking at them because I was hoping for TDs. So yeah.
Okay. So, but for the TDs, there should be a T to the power minus 5/3 decay also post maximum. I mean, this is the classic theory. So did you also look at that, whether it is did you get the falling part of the south post maximum, or is it following near to that, or it is not at all consistent?
I haven't done that. I mean, the main problem that I've had in all of these cases, and I haven't reduced all of the 34, but the main problem is that I only have one spectra. So, well, in actually quite a lot of them, there is archival, so I can compare the difference. But in a lot of them, there's just one. So I have to somehow figure out based on that one spectrum. Yeah, so that's why I'm happy that there's also additional data next to Gaia to try to combine both. But yeah, this is mostly the preliminary, and I'm working on this, and I will continue in the next few months.
Yeah. Thank you.
Okay, let's move on. Thank you very much. Thank you for this session. A big thanks to all of these 3 speakers of this session once again. It's time for coffee break. So if you want to join us for other very interesting talks, we will meet 4:10.
Sardinian time.
Sardinian time, yes. Thank you.
Sardines.
Ruszam, leci sobie. You want to go from your left?
Yeah, so I will try to connect to Zoom. It will work.
Okay. It's going to be a risky business.
No, I will be there. Well, back in,
So how many people are watching on YouTube? Do you know?
Live,
15.
no, live there's like 5 people watching, but then some people will wake up.
5 people?
Live on YouTube.
On YouTube, okay.
And there's like.
But on Zoom, now we have.
No, on the
13.
Zoom we can see. I was just wondering about YouTube.
Okay.
YouTube is mostly for recording.
Oh, okay.
It's not meant for people watching it live. Well, that's a possibility as well, but it's mostly for recording, and people can watch it anytime.
That's true. I just wanted to check if you got mine.
I think.
Yeah, you will do the second one.
Yeah.
I'll try it. We're still live. I'm not going to stop it because it's risky.
Okay, that's fine.
Don't say bad words. Should I connect to this open network?
Yeah, that's the only one we have here.
Okay, because there is Gaia 10. So.
Right.
But it's not for us. Okay.
No, I don't have Zsófia stuff. I do. Sorry. Oops.
Zsófia.
Zsófia.
Zsófia właściwie i Fia. Nadzie.
Zsófia.
Zsófia Nagy.
Tak, to jest zys.
Zys. Takie zysy to jest szy i to takie zys. Zsófia. Pewnie i tak jeszcze źle.
But you should make sure your audio is completely cut out.
Yep.
Both input and output. Otherwise, we'll get into feedback loop, infinitive. Paweł, możesz powiedzieć, bo tutaj zrobiłem rozdzielenie tych sesji, bo to były jedyne toki, jakie mieliśmy ekstragalaktyczne, a teraz mamy intragalaktyczne. Pierwotnie miałem Rupaka też w tej sesji, ale on powiedział, że to jest zła godzina dla niego, aczkolwiek teraz online. Ale w tej sesji był, razem z nimi powiedzmy. Tak, to co przeszło. A przesunąłem go na jakąś dziwną godzinę i do niczego nie pasuje. Długo przesunąłem.
No, a tu widziałem, że same są kataklizmiczne. Can I try to share the screen?
Yeah, please. You can even turn on your camera, so then we can see you speaking.
Yeah, but I don't think I will sit in front of the
You'll be there.
Yeah, it's.
I guess. How are you going to switch your slides?
With that one.
You have your own?
Yeah.
Okay, good.
Yeah, I think it will work. So.
See the nice Gaia on the camera?
Mm-hmm.
Okay, I'm going to grab a big coffee.
Yeah, that's a good idea. We don't have much time. No, we still have 20 minutes. Should I close the door?
Yeah, I think this one does right? I just put the you touch something and it works.
That's my name. I just say that.
No.
What's that?
Yeah.
Why are we seeing this?
Okay, so we should start, right?
Goes first.
Is it working?
You must be close to the microphone.
Wait.
Like this?
I'm not ready.
But what about this sound?
No, I think it's fine.
The reason of this noise is because we are too close. So when I will be there,
So,
it will be fine.
how do I change slides?
You use this magic
Okay.
ring. Put it on your finger and then press forward.
Yeah.
Actually, I will just put it on the table, I guess.
But in this way,
Oh,
because the back and forth, and the middle is red, red point,
okay.
pointer.
Oh,
Okay, so hello again after the coffee break. Now we are starting the next session about cataclysmic variables. So we have several talks in person and two poster talks, remote ones. And we will start with talk presented by Zsófia Nagy from Konkoly Observatory about Gaia alerted young eruptive star candidates. Zsófia, the floor is yours.
thank you. So you mentioned this session would be about cataclysmic variables, not exactly, or not my talk at least. So as Pavel mentioned already, I will talk about follow-up observations of Gaia alerted young eruptive star candidates. Okay, I need to get used to this too. So I will start with some introduction because probably not many of you are involved in this here. And then I will mention 3 examples of the Gaia alerted young eruptive stars that we found. I will start with 2 examples which turned out to be not eruptive but still interesting. And then I will show you 1 example of an XOR type star, which I will explain soon what it is, and then I will show you an example of a fewer type of eruptive young star. Okay. Good. So I will talk about low mass spring sequence stars here, in which case you can see in this scenario that the gas and dust fall from the envelope onto the outer disk, from where it accretes onto the stellar surface. And a fraction of this infalling matter is removed by outflows. So in this case, accretion is one of the most important physical processes. It hits the disk and increases the luminosity of the star. So apart from this sketch of how you can imagine this kind of object, the pre-main sequence star, you can see an artist's conception of it with the disk, the central star, and some accretion streams. So accretion is important, as I said, but it's not a smooth process, so it's not that easy to study. It's inhomogeneous in space and in time, and can vary by orders of magnitude, as you can see in this diagram, in the course of the life of these objects. The accretion rate can be increased by several processes like thermal or gravitational instabilities. Okay. I'm not very good at this.
I can change your slides if you want.
I pushed it like 5. You see?
Sorry.
The battery maybe.
So try it now.
Okay.
Try now.
Okay. Now it's working.
Oh, good. Thank you. Okay, so, but the change in the accretion rate is not the only process that we can take into account in the case of young stars, which complicates further this issue. So you can see here that in young stars, we have several processes going on several timescales from hours up to centuries. And the typical amplitudes are between a few, are up to like 6 magnitudes. So the two main processes are still the accretion and circumstellar extinction. And accretion-related processes here are shown with blue, and those which are related to the circumstellar extinction are shown with red. So in this talk, I'm interested in those processes or those young stars where the brightness variations are related to the change in the accretion rate. But as I mentioned, it's quite hard to distinguish between these. Okay. So I will focus on eruptive young stars, which we want to study because we can learn about the entire star formation process. We think, as I mentioned, that a star formation or the accretion in star formation is not continuous. It's going on in these episodes, in kind of episodic star formation, episodic accretion. So for studying this, we need to find these eruptive young stars. Here you see some typical light curves of eruptive young stars. There are two main types. For the long-term outbursts, we have fjords or FU Orionis type objects. And by long-term, I mean centuries or decades up to a century. And the short-term outbursts are XORs. And by short-term, I mean the outburst event is a few months up to a year, and it's reoccurring. It occurs in once every few years. And about fjords, in such long outbursts, we haven't actually seen any fjord to fade. So that's still to happen, and it would be quite exciting if we can find such an example. So just to summarize the properties of fjords and XORs, as I said, the timescales are different for the outburst, but also the optical burst strength. It's stronger a bit for fjords than for XORs. The accretion rates are also higher for fjords than for XORs, but already for XORs, they are typically higher than for the classical T Taurus stars. The most important difference is their spectra, because in the beginning of the outburst, we still don't know the time scale. And in that case, we need spectroscopy to be able to distinguish between these two types, because for fjords, we see a predominantly absorption line spectrum, while XORs exhibit an emission line spectrum. Okay. Okay, so this is just some examples of the spectra of these young eruptive stars. Like in the upper figure, you see in the K-band, the typical XOR spectrum and the typical fjord spectrum. The fjord here was one of the first fjords that we identified in our group. And then you see the H-band continuum, which has this triangular shape for fjords due to water vapor bands. So this is something that we can also use to identify such sources. And the more cases we discover, the more we know that there are some intermediate types. So that's also something that we need to learn about. Sorry about this. Okay, so why do we need to do this, this kind of project? We only know about 50 eruptive young stars, and to really have the statistics to learn more about these, we need to find some new cases, and for that, the Gaia alert system is one of the best tools now. So what we are looking for is when there is candidate YSO, which brightens, or when there is a YSO, like a confirmed YSO,
which starts to fade. And that's because, as I mentioned, for fjords, we haven't seen any of them which finished its outburst. So what do we use to identify such cases? Okay. So after the Gaia alert, we get all the archival data there is for these sources, like from WISE or ZTF or PenStars. We can create the SCDs and the near-infrared color diagrams as well. In some cases, these stars are related to some star-forming regions where we have the distance, then it's easy. Sometimes we don't know even the distance, but mostly we need confirmation as a follow-up spectroscopy. Photometry as well, of course. We use for photometry mostly telescopes from Hungary and Poland, Mount Suhora. And for the southern targets, we use the RAM, which we heard about earlier today, and telescopes in South Africa as well. For spectroscopy, we use the NOT, the TNG, GTC many times, Liverpool telescope that you're quite familiar with, NTT, LBT, and I will show some spectra from the VLT and from Gemini as well. So until now, I show this slide always at this kind of meetings, and the numbers are actually increasing, luckily. So we have selected about 80 eruptive young star candidates. Not all of them turned out to be eruptive young stars. One of them, Jaroslav, will tell you about soon. But most of them, I would say. We have follow-up spectroscopy for more than 20 targets and follow-up photometry for even more. And we already published some papers on some targets. We just submitted one on a new XOR, and we are preparing some more papers. So I will show you some results from 3 of these papers. Okay, so in this case, the time scale for these sources, as you see in these light curves, is about 1 year for the brightening. However, the amplitude of the brightening turned out to be similar to XORs for only one of the targets. For the other target, it's a lot less. It's about 0.5 magnitude. But still, we observed some follow-up spectroscopy for both targets to be able to see whether like one of them is an XOR or, you know, if the brightening in general is related to accretion rate change. So we use the TNG in both cases, and for Gaia 20FGX, the one with the larger amplitude, we observed another spectrum with the GTC. So in their spectra, we observed some tracers of the accretion rate, like the Balmer lines and bracket gamma, so we could derive the accretion parameters. We derived accretion luminosities and accretion rates that you can see here. On the left-hand side, the accretion luminosities are plotted against the stellar luminosities. And on the right-hand side, the accretion rates are plotted against the stellar masses. And all these small dots correspond to T Tauri stars, classical T Tauri stars from earlier surveys, where you can see this linear trend. With the triangles, there are some confirmed XORs, and with the asterisks, you see our sources. We have 2 epochs, as I mentioned, for one of them. So what we got is that, so the accretion rates for these sources are actually more typical or closer to classical T Tauri stars. However, the time scale of these episodes is definitely not typical of classical T Tauri stars. So what we have is something which is not as powerful as an XOR, but something that is really similar in its light curve. So maybe it's like a new type of object. We need to find some more of these cases to be able to know whether this is like a class of sources, actually. So as I mentioned, we just discovered, or we just submitted a paper for discovery of a new XOR. This was a known YSO in the literature. there are some papers which investigate its parameters. We knew that it had an outflow from CO data. And then there was a Gaia alert due to a 4 magnitude brightening. However, as you can see in this light curve as well, several optical and near-infrared data points, there are at least 5 brightening episodes since 2015, which is what we expect from an XOR. So we obtained follow-up spectra. This is the one from Gemini South, I believe. And we observed a spectrum, emission line dominated spectrum that we can expect for XORs. We see some tracers of the accretion rate. We could measure the accretion rate, which is in the range of XORs. And we also see an indication of a jet like H2 lines. So this paper should soon be on archive. And I mentioned that, one of the kind of sources that we are interested in is a fjord which is about to end its outburst. And we have seen a few Gaia alerts like this, and this is one of them, which is quite promising. So it's Gaia 21 ELV, and on the left-hand side, you see its long-term light curve. In the 70s, I believe it brightened from archival data, and then it stayed in the bright state for decades. And then in 2021, or a little bit earlier, it started fading. So Gaia alert happened toward the end of 2021. We already had some spectroscopy from Gemini for it. And then we obtained another spectrum from the LTX shooter. And our data actually confirmed that this is a fjord. So it was known to be an outburst young stellar object, but our data provide the first spectroscopic confirmation of it. And at the moment, it's still a work in progress, whether if the fading is related to the decrease of the accretion rate or some other processes like circumstellar extinction. But based on the preliminary results, it's probably a decrease in the accretion rate. Another question is if it will stay like that or if it will brighten again. That we will see from the Gaia light curve. So just a summary, I hope I showed you that Gaia alerts are also a useful tool for identifying young eruptive stars. We are taking spectroscopic follow-up observations in order to classify these sources. I showed you 2 sources which turned out to be classical T-Taurus stars, but rather a peculiar kind, and another source which is a new XOR, and another source which will hopefully be confirmed in the coming months to be a fading fjord. And I just would like to show this plot again about timescales and amplitudes of young stellar object, because this is basically the goal, to be able to populate this diagram more and to understand whether there are subclasses here. So that's it. Thank you.
Thank you very much. Thank you for the nice talk. It's time for questions. Carolina.
Hi, Zsófia. Very nice talk. Thank you. I want to ask you about the procedure, because it is difficult to distinguish based on Gaia alerts these objects from, for example, classical novae outbursts. And what is the approach? What, rather cautious that you are almost certain that the objects are young stellar objects, and then you start the follow-up spectroscopy, and it is risky because you can omit many interesting cases, or rather it is that way that almost everything what is suspected to be young stellar object is observed further on spectroscopically.
So I didn't mention, but there was a paper on quite a large number of YSOs by Gábor Marton, his name was mentioned earlier, and he calculated some probabilities based on SCDs and other data, on what is the probability of a source to be a YSO. So we use that as well. And as I mentioned, we take all the information like colors and the distance and, whether it's related to a star forming region. So, I would say most of the spectra that we take turn out to be VSOs, just maybe not eruptive. However, some of those sources turn out to be something different. And I think that's the next talk where you will see such an example. But yeah, I think we are trying to be quite cautious in terms of, you know, what we collect data for. Yeah, but of course it's not 100% sure.
Okay, Simon, please.
Really nice. I'm curious about, I had to write, Gaia 21 ELB.
Yes.
Where you have this historic data from, is that from photographic plates?
Yes, exactly. The earliest data points are photographic plates. Yeah.
So the obvious thing to do, and I wanted to do but never did it because I'm scared of the false alarm rate, would be to take a historic catalogue and look for things that are much, much brighter in Gaia, rather than waiting for things to fade in the alerts. Just do a difference between Gaia EDR3 and DSS, and look for things that are significantly different in brightness. Is anyone in your group thinking of that? Would you like to?
This is a really great idea, but at the moment we are not doing this. So this is a really particular case. It was really lucky that, you know, all these data were accumulated before. But yeah, we should consider doing this actually.
We'll have a chat.
Do we have any questions on Zoom? Łukasz?
No.
No? Okay, so thank you very much, Zsófia. And now, sorry for this noise. And now Elmé Breedt from Cambridge University will tell us about accreting white dwarfs. So it's time for real cataclysmic variables or related objects. 15 minutes. Okay? That's a good question. I think now let's start.
Right. As Simon mentioned this morning, I'm one of the people who work on eyeballing and publishing these alerts. So it's really exciting to see, you know, how many of these alerts are followed up across the various categories. So I almost want to say thank you for that. But it's just really great to see all the work that's been going on. I'm going to talk about accreting white dwarfs in the Gaia alerts, and I'll start with this illustration of what these cataclysmic variables look like. They consist of a white dwarf accreting from a main sequence star via an accretion disk at orbital periods of between 80 minutes and around 9 or 10 hours. So they're fairly compact binaries. I like showing illustrations like this, pictures like this, because it really shows just how much potential there is for variability in these objects. And you can have the white dwarf or the companion star varying by pulsations or flares. There can be geometric variability like eclipses or ellipsoidal modulation as the binary rotates around. There's the bright spot at the edge of the accretion disk where the gas stream hits the disk. And then, of course, the accretion disk itself. And the accretion disk is subject to a thermal instability, which cause semi-regular outbursts in the disk of, 5 or 6 magnitude, so a factor of 100 in flux in the space of less than a day. And that's what make these binaries appear in alerts, in Gaia alerts or other transient surveys, is these regular disk outbursts that appear. The very first one to be discovered was UGEM in 1855. And you can see the light curve there in the top right-hand corner as it brightens from 14th magnitude to 9th magnitude every 120 days or so. So here I'm showing the number of CVs known versus the year in which they were discovered. You see UGEM there in 1855. And then it took a full 41 years before the next example was discovered, the famous SS Cygni. From then on, it was a slow increase in numbers, and it was not until the early 1980s before we had this model of what they are, white dwarf accreting from a companion. The first sort of increase real increase in numbers came with SDSS, the spectra that SDSS produced. And then this huge increase in numbers came from transient surveys or wide area photometric surveys like Gaia, CRTS, Assassin, ZTF, and a whole lot of others. And you can see that that's really ramped up the number of known cataclysmic variables. So what I'm going to be talking about is what's the value of these cataclysmic, of these transient surveys, what we can learn from them, and then about Gaia Alert itself, and then a little bit on time series follow-up of some of these events. So what I'm showing here is just some example light curves. These are from CRTS, but they could as well have been from Gaia, just to show the variety in behavior that we see in these systems. Some have very frequent outbursts, some less so, like the one in the bottom left, and others, like the one in the bottom right, have just had one outburst in the 7.5 years that CRTS was observing these systems. Then there are others that are only observed or only seen in outbursts. The one on the top right there, the gray points or the photometric upper limits for every night that field was observed. And you can see the black points there that the CV was only seen when it was in outburst. But we can go to surveys like SDSS or PanSTARRS that have deeper photometry and look for the object at that position just to get a handle on what the quiescent magnitudes of these objects are. And you can see that in the right-hand panels. The one at the top left there has a SDSS source at 22.3 magnitudes, which is below the Gaia detection limit. So that's one of the advantages of using transient surveys, is that we can find CVs or find systems that are fainter than the nominal detection limit of these surveys. So if you have a detection limit of say 20th magnitude with outburst amplitudes of 5 or 6 magnitudes, it means that in principle we can detect CVs that are as faint as 25 or 26 magnitudes in their quiescence, which would not otherwise be possible. But the interesting thing with CRTS is that of the sort of 600 or so CVs in the SDSS footprint, there was only a single one which did not have an SDSS counterpart. And so that, I think, means that you were looking out towards the edge of their distribution in the galaxy, out into the thick disk. You have to be careful though, because CRTS was looking out of the galaxy, it wasn't observing in the galactic plane. And so with Gaia, it will be a little bit different, where we actually do look into the galaxy as well. So we'll have to see how that statement stands out, but that's definitely something I wish to explore some more, and I don't have an answer to that yet. The outbursts, or the number of outbursts, are related to the accretion rate in the CV. So here I'm plotting the number of outbursts in the light curve against the discovery date of the CV. The colors there are just to guide the eye. It's just in year-long bins. The colors don't really mean anything. And what this shows is when the CVs were discovered and the number of outbursts they've had. So there's an obvious bias here. So systems with more frequent outbursts will have a higher likelihood of being discovered. So they'll be discovered early on. And try that one, thank you. So the systems with more frequent outbursts will be discovered early on, and by now they've had many outbursts towards the end of their survey date, and that's why we get this sort of slope in this plot. But the main thing to look out for here is to notice that the sample is dominated by systems with just a single outburst in the 6 years. If we plot that as a cumulative distribution, we see that systems with more outbursts rise quickly. Does this have a, no, okay, sorry. Does this have a, systems with more outbursts rise early on in the survey in this cumulative distribution, but the distribution also flattens off quite quickly. Systems with higher accretion rates are found earlier in the survey, and towards the end of the survey, no more high accretion rate CVs were found. And compare that to the black line at the bottom, that's the ones with just a single outburst, that just keeps increasing steeply and will likely continue increasing like that until, for several years, especially considering that there are many more years or how long the interval between successive outbursts are in these systems. So fortunately with this audience, I don't have to convince you about the value of Gaia alerts. So just quickly over here, I've had 17,500 alerts until September last year. As you've heard several times, it's 21,500 today. Simon already showed this plot earlier today. The alerts as a whole are published at around 11 alerts per day. And these CV and CV candidates are about 10 per week that we found in the alerts. Now, classification and follow-up remains to be one of the most challenging things to do for surveys like this, and especially for deep surveys like Gaia alerts. And you can see this observer telling its colleague, says, actually, they all just look alike to me. And there certainly are days where it feels like that they all just look alike. But this is where the time series follow-up comes in. It's the follow-up at different timescales that show us what the difference in these different types of alerts are. Unfortunately, with Gaia, gives us a lot of extra information as well. The BPRP spectra, I'm showing here various classified alerts. This first one is something with a disk outburst, and there's some bonus eclipses in there as well. There's type 1a supernova decaying, a YSO, and a microlensing event. And if you look at the spectra below it, there's some clear differences in the spectra. So we find that these light curves and spectra are the most important things in classifying these alerts, but also the contextual information, things like how close it is to another galaxy or a YSO in a star-forming region, and things like that. That also helps a lot. But there is still some confusion between CVs and young type 1a supernovae, and that slightly biases the training sample. But this is what the contents of the Gaia alerts look like. And this is based on not so much machine learning, but rather cross-matching with different wavelengths and as I say, all this contextual information of various systems. This plot is actually a bit of a cheat because each of those colors represent the sources that are classified as well as the candidates for the system. So for example, the supernovae you see there in purple, that's the confirmed supernovae as well as the candidate supernovae. So the plot should actually look something like this, where the darker colors on the inner circle represent the confirmed candidates and the lighter colors, the candidates. And that's the same for all of them. But since that is a bit complicated, I'm just going to go back to this one and we'll look at that first. So supernovae are the most common among the alerts, about 41% of them. Then there's some smaller categories here at the bottom, stellar objects. We still have a lot of unknowns. So even within this classification, there's still like 23.5% of the alerts are completely unknown. So that's still something to work on. What they are. And then the AGN or QSOs, and CVs are more or less the same at 13 to 14% of the alerts. The Gaia CVs as a population is still a bit of a work in progress. But what I find interesting is that among all the CVs and CV candidates detected, about 50% of them were detected by Gaia first. So it's not known systems that were rediscovered due to their outburst by Gaia, but systems that was first seen by Gaia. I'm just going to quickly go into some of the interesting discoveries in Gaia alerts and talk about the AMCVN stars. AMCVNs are basically helium cataclysmic variables. They are even more compact than the hydrogen CVs themselves, so they have periods of between 5 and 70 minutes. The first one was the Gaia 14 AAE, which is the first alert ever discovered by or published by Gaia. And that was the first fully eclipsing AMCVN system that was ever found. And that one will still be observed for a long time to come. But I want to focus on that spectrum. Well, I can show you some of these spectra here. I don't know if you can see the green lines. The green lines there are the wavelengths of hydrogen. The purple lines are the wavelengths of helium. And where the hydrogen wavelengths are, there is nothing in the spectra, but at the helium lines, you can see some emission lines in this system. So the optical spectra are completely free of any hydrogen. But I want to focus on the top one there, Gaia 16 ALL, as one of the Gaia discoveries. You can already tell from the spectrum that it's very faint and not that easy to see. It's Gaia alerts light curve. It's about 20.5 in quiescence, but you can see that it really outbursts very, very frequently. And because it's so faint, and if it's something that has a very short orbital period, it's very difficult to measure these things in phased resolve spectroscopy. It's almost even on the largest telescope, so it becomes really hard to measure the orbital periods. But fortunately for us, this object was covered by TESS, and it was in one of these very frequently observed areas of TESS at the bottom here. And so it was covered in many TESS sectors. And that's the TESS light curve that comes out of it. At quiescence, it's too faint for TESS to see, but when it goes into outburst, this is what's detected by TESS. And you can see these broad outbursts with a dip initial. Thanks. Oh, this is quieter. Thanks. So you can see the broad outbursts in the. You can see the outbursts in these light curves over there, and the shorter outbursts that are called rebrightenings in the accretion disk. And from this, during these bright super outbursts, the disk displays super humps, and from that the orbital period can be measured. And so that was measured to be 30.14 minutes for the system, and it's actually one of the longest period AMCVNs that shows these super outbursts and rebrightenings, and it further links the AMCVNs to the hydrogen CV, showing that it's the same process operating in both of these systems. Just a quick summary. The transient surveys are a very efficient way of finding the faintest members of the cataclysmic variable population. The CRTS samples show that the population is dominated by low accretion rate CVs.
there are many more low accretion rate CVs, and we need to convert that to a space density with the Gaia data. And in addition to the time domain follow-up, there's value in combining data from various surveys to get to this. Thanks very much.
Thank you very much. Thank you, Elmé, for a nice talk. So I'm sorry for the problems with the sound, especially for Zoom participants. It's even worse probably, but I guess it's not our fault. Let's try to take some questions from here. Any questions, Carolina?
Elmé, about the last star you showed us, the very interesting ASVM. Do you have any campaign monitoring this object, this frequent outburst, super outburst activity?
Personally, I don't. It's quite tricky. I did try in the beginning, just after I discovered it. I have a spectrum of it, which was just from some follow-up at the NTT. But I don't have any specific follow-up of this one. It's quite tricky to monitor because even the outbursts you see there are sometimes quite short-lived, and by the time we see an outburst, I keep checking the Gaia alerts light curve, but by the time we see that it's an outburst, to then find the telescope that's available. The thing is also it's very far south. I think it's minus 75 declination or something. So there's not a lot of telescopes available that can reach that far.
And what is the luminosity in percents?
20.5.
Yeah.
Łukasz?
This is a perfect case for black hole storm. You just enter it there and you tell people this is an important target. And whenever people can, they observe it. If they observe it on a random basis, then you will sometimes get quiescence, sometimes you get an outburst, but at least you will know that something's going on. So definitely, and I love the name of it. It says it all.
It says it all, yeah. No, thanks, I'll definitely do that. I'll come to tomorrow's sessions as well. Something that outbursts as frequently as this, you're bound to find it in outbursts at some point.
Excellent.
More questions? Maybe on Zoom?
Nope.
No questions on Zoom? Okay, so thank you very much again. And now it's time for Jaroslav Merc from Charles University.
It's going to be tricky.
Yes.
More fun.
You can share your screen. As you see, Jaroslav likes number 1 because it will be about first symbiotic nova and first extragalactic symbiotic star. Jaroslav, you can start if you are ready.
I'm ready. I hope the microphone is ready for this. So, yes, it's working. So thank you very much. As you have heard, I am Jaroslav Merc. I finished my PhD actually 1 month ago, and now I'm working at the Astronomical Institute of Charles University in Prague, in Czech Republic. And I will continue in the topic which was already started. It's accreting white dwarfs, but I will get to bigger things because I will talk about symbiotic binaries. And I will very shortly introduce symbiotic binaries. So also similar to CVs, these are strongly interacting binaries, but there is a big difference between CVs and symbiotic binaries in that sense that symbiotic binaries are among the widest interacting systems. We're talking about orbital periods of hundreds of days, not minutes, as was the case for CVs. So mostly these are open binaries. One of the components of symbiotic binaries, in strong contrast with CVs, it's cool giant star, and the second one is mostly a white dwarf, but there are cases where you have also neutron star accreter, but it's a bit more difficult. And you have a lot of material all around, which is creating the nebula, and then you have all these nice emission lines in spectra and so on. And in most cases, probably the mass is transferred via stellar wind, but in some cases also the giant can fill its Roche lobe, so you have a Roche lobe overflow. And now I will just mention a few points why this study of I am now presenting on this conference is interesting. The first of all, of course, everyone will say that about the objects they like. So I will say also about symbiotics that they are unique astrophysical laboratories in the study of many astrophysical processes like accretion, winds, outbursts, jets, and so on. And they are also important for binary evolution and understanding the binaries. If not for other reasons, they were suggested as supernova 1A progenitor candidates. So also from this sense, they are interesting. And also during my PhD, I created an online database of symbiotic variables because the last catalogs were 20 years old. So I created a new one. And actually there are just 291 confirmed symbiotic stars in our galaxy. And this is really in a huge contrast with number of expected symbiotic stars in our galaxy, which are somewhere in the range of 10 to 3, so thousands to maybe hundreds of thousands of symbiotic stars, which should be in our galaxy. So it's nice when we have some ways how to discover new ones to understand the population as a whole. And actually, Gaia can help us with this task. Because several of the known symbiotic stars were already detected by Gaia in brightening. And I will not mention all of them because I talked about this last year. I will just mention 2 of them with these nice Gaia names. And I am mentioning these 2 for the reason that in both cases, Gaia detected the first ever recorded outburst of these symbiotic stars. So also for known symbiotic stars, we can have a nice new information on these objects. So these 2 were known before, but recorded in outbursts. And the talk I gave 2 years ago actually was about the Gaia 18 AEN, which was previously known only as an emission line star. So this brightening of this emission line star was announced as Gaia Science Alert. And actually, we did a lot of work on this object and we found out that it's a symbiotic star. And this one is actually the first symbiotic star discovered by Gaia. So that's a paper we published in 2020. So Gaia can do that. And now I will continue on collecting these firsts in this talk. So the idea was to search for another outbursting symbiotic stars which are unknown in Gaia Science Alerts. Because as we have heard several times, many of Gaia Science Alerts are still unclassified. So maybe there are some among them, some symbiotic stars among them. So last year I talked a bit about selecting of the promising candidates. I will not cover this this year. I will just say that we applied several selection criteria, which are in some cases not working that well because it's not that easy, but we used position in HR diagram, infrared colors, we look for the brightening amplitude and the general shape of the light current and so on. And we selected some candidates which are more or less promising and could be symbiotic stars. And actually in this list, there are 2 I will speak about today. The first one is Gaia 17 BHG, which was actually not only included in my list, but previously it was classified as a possible symbiotic nova by Williams et al. Because they obtained some follow-up of the brightening published in Gaia Science Alert. And the second one is Gaia 19 BPG, which also passed my criteria on symbiotic stars in the Gaia Science Alerts. But actually, that's the object about which Zsófia spoke. It was suspected first as an eruptive young stellar object. So they did a lot of work before I selected this object. And that's actually a very nice example that these workshops are perfect for creating these collaborations because we spoke together during the coffee break last year in Heraklion she came to me and said that they have something which might be interesting, and we actually find out that it's really an interesting object, and it's the object I really like. So you will see some of the results of the collaboration which started at this meeting last year. So first I will focus on the one which was observed by Gaia in 2017, and this brightening was announced in May 2017, and in the alert itself it's described as a Gaia source which brightens by 0.7 magnitude, and it's located somewhere in the region of galaxy M31. And Williams et al. Obtained multicolor photometry and low-res spectra using Liverpool telescope. And that's basically all the information which is available for this object, because it's quite faint. In the astronomers' telegram itself, they describe this object as a symbiotic nova, possible symbiotic nova in eruption, which is a similar kind to these stars which are mentioned on the slide. It's not true, actually. But we used the spectroscopy they obtained. We downloaded it from archive, and we used photometry from Gaia to somehow analyze this object. And what is the conclusion from that is that really there was an outburst of this object, and this red point, which you see, is when the alert was published. So actually the outburst continued also after the alert was published, and the light curve showed some outbursts of 1.6 magnitude in the G filter. The rise to the maximum took about 4 months, and then it was followed by some 1 year long decline and some rebrightening afterwards. And some kind of pre-outburst brightness was then reached after 3 years and 3 months roughly. And this is actually not a behavior of a symbiotic nova. Therefore, I said that it's not a symbiotic nova as it was suggested before. And actually, these RS of Yuhi or TSRB are not symbiotic nova as we call them, but they are a symbiotic recurrent novae. But also, in this case, this is not a photometric behavior of a symbiotic recurrent nova. So we also looked at the spectra, and the spectra are obtained close to the outburst maximum. And what you can see is there are a lot of emission lines, and you cannot read what kind of emission lines are there, but there are Balmer lines, there are also a prominent line of helium, and also of neutron and ionized helium, and possibly there is also O3. And that's a quite typical appearance of a symbiotic star in outburst, but not of a symbiotic nova again, but of a classical symbiotic star in outburst. What is a small thing to mention is that from this spectrum, the presence of the cool component itself is not apparent very well, because usually you can see molecular bands in the red part because it's a cool star. But this could be first low signal to noise because it's a very faint star, but also during the outburst you have a lot of radiation coming from a nebula and or the hot component. So this contribution of a red giant is then not visible. But if this is a star in M31, the presence of a cool giant is well subverted by the luminosity. So the general conclusion from this is that Gaia 17 BHG is actually a symbiotic star, and it would be, I will just find some place in space where this is not that much interrupted. It's not this, maybe here. So that Gaia 17 BHG is a symbiotic star, not a symbiotic nova, but a classical symbiotic star, and it would be classified as the first extragalactic symbiotic star discovered by Gaia. The second object is Gaia 19 BPG, which was also published as a Gaia Science Alert. This one is in April 2019, and it was described as a red galactic plane source which brightens by 1.5 magnitude over 8 months. And as it was selected as a possible eruptive young stellar object, we have an extensive follow-up, which was obtained by the group of Hungarians from Konkoly Observatory. So we have photometry from Gaia, we have photometry from ZTF. Now,
Might be a different mic doing this.
Yeah, but
it's not this mic.
I'm off. It's maybe my head or so. So we have photometry from Gaia, ZVF, Konkoly Observatory, Zsófia, and I have downloaded also the data from Black Hole Tom. You will see. We cannot use Assassin because there is a bright star very nearby. This red one is our target, and this one is just outshining the Assassin data because of the big pixels. And we have also infrared photometry, single observation. And we have a lot of interesting spectroscopic information on this object. We have some low resolution spectra obtained in 2019, 2020, 2021, and actually 2022 from amateur observers. We have some medium resolution optical spectra from LBT from 2021. And actually last month, we also were successful to obtain the observations using NOT. And we have a high-res spectra of H-alpha region from April 2021 from GTC. We have infrared spectroscopy from several occasions, and we have amateur near-infrared spectrum from this summer. So we have quite a lot of material. I will start not with this observing material we have, but what is available in archives, because the first thing we just looked for was if there is really a giant in the system, because that's what is important for symbiotic classification. Gaia DR3 data really suggests that there is a giant, because the star is this red one here. It's located in the region of HR diagram where giants are, and these blue ones are known symbiotic stars. So it's located in a nice region where you would expect to have a symbiotic star. But given that we have also infrared spectra, we can use luminosity diagnostic, which is based on infrared data, because there is this nice value which you can obtain from the infrared spectra, which would help you to distinguish between main sequence stars or dwarfs and giants. And actually, here are main sequence stars, here you have giants, and all three spectra, when you measure this value from the infrared spectra, confirms that we really have a giant in the system. So that's very promising to study further, because we have something which is a red giant in outbursts. So now I will show you also that from the archival data, you can obtain some rough estimate of the temperature of this source. Because the archival data are showing that we have a cool giant in the system. Not only that we have a giant, but we have a cool giant, because the pre-outburst spectral energy distribution is consistent roughly with the temperature. Now that's definitely bad with microphone. Yeah, so we have a source which is really consistent with a cool star, and moreover, we have some observations even with very low resolution from Gaia, but even with this very low resolution, you can see in the pre-outburst data molecular advance. So this confirms that we have a very low temperature source in the system. During the outburst, we have this set is dominated with a hotter source, which is temperature just from few observations, not well constrained, but there is something which is much hotter than it was during the pre-outburst stage or before the outburst. So finally, I will show you the light curve. And if you remember the light curves of these young eruptive stars, that's, yeah, in a sense, it's a bit similar to that. So you have nothing, and then you have some rise to the maximum. And actually, again, there is a red point just there, and that's the time when the Gaia Science Alert was published. So actually, the outburst started somewhere in maybe November 2018. And now I will show you also the other data, because it's very nice that we have quite a lot of follow-up. So we from all this data, we know that there was some kind of steeper rise for about 1 year, let's say, but then there was some continuation of the rise towards the maximum magnitude also for another, let's say, 20 months. So the total magnitude of the outburst was about 3 in Gaia G filter, 5 in ZTF, G, and R filters. And what is also important or interesting for symbiotic classification, that the source became slightly bluer during the rise towards the maximum. And then what you saw is that there is some dip in the light curve, which looks like an eclipse or some kind of stuff. And it's even better visible when you just look for the color evolution. So this is G minus R color, and you see that then there is a really significant change of the color of the object, and you have significantly redder colors. And that would suggest that it is an eclipse of the hot star, which is present in the system by the cool star. And that's something which is actually quite often seen in symbiotic binaries, or especially during the symbiotic nova outburst, that you have dip in brightness during the eclipse. So now I will finish this with what we see in spectroscopy. In 2018, 19 and 20, when the low-res spectra were obtained, this is one from 2019, only Palmer lines were in emission. That's not actually enough for symbiotic classification. But it is a typical appearance of symbiotic nova in a maximum. The problem with symbiotic nova is that you need to wait for a long time for them to evolve, because they are very slow. But in maximum, they look like this, so it was quite promising. What is even more promising is that they actually obtained also high-res spectrum of H alpha, and this is this green color here, and you see very nicely this blue shifted absorption, which is very typical for symbiotic stars, because you have a wind of the giant, so there is a comparison with Bayes Mon spectrum. And this is very often seen in symbiotic stars. So that's another plus for the symbiotic classification. And then I think that this problem was solved with late 2021 and 2022 spectra, because the appearance changed very rapidly. And maybe this eclipsing process helped us that we were able to see this earlier than we would see that without the eclipse. So we have a lot of emission lines of hydrogen and helium, and also of ionized iron and titanium and stuff like that, which you would expect from a symbiotic nova. So this one seems to be behaving nicely. What is also interesting is that when we measure the equivalent width of H alpha, it was during that time in late 21 and also in summer 22, signitightly higher than it was before. 20 times in comparison with 2019, and 200 times in comparison with 2020. So really nice things are going on in the system. So I will conclude that this star is actually a first slow symbiotic nova discovered by Gaia, and from what we already obtained, I'm pretty sure, and definitely this will be confirmed maybe in 20 or 30 years when all these nice emission lines of high ionization potential will appear. But I'm pretty sure that we have this right, because it's behaving very nicely. So I will just conclude with one point, and it's that some unknown outbursting symbiotic stars still might be hidden among the Gaia Science alerts, and we have some list of candidates to do the spectroscopic follow-up, mostly because that's the most important. And this claim is based on 3 examples we have already. So this is a collection of Gaia's first symbiotic star, galactic, first extragalactic, and first slow symbiotic nova. The only thing we are missing is the first recurrent symbiotic nova. But the problem with those is that their outbursts are very slow. And actually, there is one known symbiotic recurrent nova, which was observed by Gaia in the outburst. But there is just one point in the whole light curve, which is just above average. So it would be very difficult to complete this with this list with the first symbiotic recurrent nova discovered by Gaia. And with that, I will thank for for the attention. Thank you very much. Nice first. So it's time for questions. Milena? 2 microphones works well. 3, it's too much. Let's try.
Okay, it works. So I was wondering if RVS data, so any spectroscopic data that will be or are given by Gaia will be somehow useful. I know the range, the wavelength range is pretty, like it's not large. So I was wondering if that could be of any help in your research.
Yeah, I don't think that they will help much for searching for symbiotic stars. They can help, of course, in somehow characterizing these objects. But for searching, if you just would have some median spectrum, I don't think that they will be of much help. Just a little. Then, if you will have some time series of those, you can use them for somehow understanding what is going on with variability, because actually there is a mess in this sense that you in the light curves you can see the orbital response, and in some cases you just see the pulsations. So I think that radial velocities could help with this a lot. Okay, the last question from Josh.
Hi. I have observed symbiotic stars for Ulysses Munari for some time. I can offer BVI or BVRI images from the southern hemisphere from my remote observation in Chile, if of interest.
Yeah, of course, that would be great. I think that your observations of this first slow symbiotic nova are in Black Hole Tom. Yeah, I think so, that I saw the name. Yeah, I remember this name as well, so probably you're right. Okay, thank you very much, Jaro. And now we have 2 virtual talks prepared by 2 students from Nicolaus Copernicus University, supervised by Karolina Bąkowska, who is here. There will be about the posters. You can see these posters on the wall in our room. So the first speaker is Bartosz Kirpluk, and he's going to tell us a few words about ER Ursa Majoris. Bartosz, are you there?
Yes.
Okay, so you can share your screen. Okay, you can start if you are ready.
Hello, I'm Bartosz Kirpluk from Nicolaus Copernicus University in Toruń. Today I would like to present some results for cataclysmic variable star ER Ursa Majoris. At the beginning, I will present the 60 centimeters telescope. The telescope is located. It was installed almost 30 years ago and recently was renovated with the recoating of the mirror. Cataclysmic variable star is a binary system which with mass transfer. Mass accretion between components causes a sudden brightening called super outburst. The time between 2 consecutive super outbursts is called the supercycle length. The AAVSO data is collected by amateur astronomers, and they are different quality. Some parts of the lag curve have a caps that don't allow us to derive the length of the supercycle. This problem was solved by fitting a Bézier curve to the complete super outburst and putting its shape on the incomplete super outburst. Data collected by amateurs astronomers are marked by blue dots and they were scattered. Fortunately, we had amount a good nights in Piwnice, especially in March, and these data are marked with purple dots. After Bézier curve fitting, which I talked about in the previous slide, we were able to determine the length of the supercycle in this case. In January 2022, the test satellite observed the Ursa Majoris super outburst, and this data is marked with green dots. In March 2022, we observed a consecutive super outburst in the Piwnice observatory. These data were used to determine the most actual supercycle length in early 2022, which is 14 days. By a straight line fit, we see elongation of the supercycle length by 1 day every 5 years. Super outbursts are occurring rarer, and the mass transfer between components is dropping. The most recently results on the right side. They are not located around 55 days, but they are the value as at the beginning of the monitoring 13 years ago. So we'll continue monitoring the changes of the supercycle length in the future. Recently, we had an idea of the Ursa Majoris simultaneous observation in radio and visual frequencies. We will use the 32-meter radio telescope in the Piwnice Observatory. We would like to compare the behavior of Ursa Majoris during super outburst in radio and visual frequencies. This is all. Thank you for attention.
Thank you very much. We don't have time for questions, so let's move to the next speaker. Mateusz Motyliński will will show us a few slides and tell us a few words about another variable, Px Andromeda. Mateusz, are you?
Okay, can you hear me?
Yes, but we don't see your slides.
Okay, wait a second. Okay.
Starting.
Okay, you see it or no?
No, not yet. We don't see your slide, only Blackboard.
Okay, wait.
You have to click the green button below.
Yes, I know, but...
And then yeah, you must choose the full screen. I guess it will be the easiest way, and then make the full screen.
Okay, but I don't have an option for full screen. Only whiteboard or.
What do you use? PowerPoint or LibreOffice or something else?
I have a PDF of it.
Yeah.
I have his slides. So.
Okay, we have your slides, so we can show it. Wait a minute, please.
Okay.
I have to share my screen.
Okay. Okay, so your slides should be visible.
Okay.
I'm going to change.
Yeah, we will be changing. Just let us know.
Okay.
So we can start.
Okay. My presentation is about poster study of cataclysmic variable peaks Andromeda based on photometric observation. But our studies basically focused on eclipses of this star. So next, please. First of all, we used the 19 centimeters telescope in the Institute of Astronomy of the Nicolaus Copernicus University in Piwnice near Toruń to observe PX and main mirror last year recoated and telescope had renovated. Next, please. So we uploaded the observation from Piwnice to Black Hole Tom, and the photometry provided by Black Hole Tom is extraordinarily good. As you can see, the eclipse are clearly visible in the end of light curve. Hence, we will continue proceed data in Black Hole Tom, but no longer in Astronomy J. Next, please. Okay, a significant part of data are from amateurs telescopes. This is an example light curve from American Association of Variable Star Observers. Unfortunately, not all of data are of such good quality as this example. So we had to select the best eclipses from the database. Next, please. Well, as a result, we obtained the OC diagram for eclipses for over 30 years of observation. The last blue triangles are from Piwnice observation. The two black squares from TESS satellite. The dots green, orange, yellow, and pink are from amateurs telescopes. And the last red and purple are from publications. One's red are from Stanishev from 2002, and purple from Hallier 1994. we do not observe for this data any change of orbital period of maxent. Next, please. And this is it. Thank you very much. And for more details and future work, I invite you to read the poster. Thank you very much.
Thank you very much, Mateusz. Nice work. Thank you, guys. A big thanks to all of the speakers of the last session today. Thank you, Łukasz, for your help. My assistant. Okay, it was quite long day, so I think we are ready to take some break. Thank you very much.
Just a technical announcement. So, of course, thank you to the chair people today. And tomorrow, hope the microphones will work better tomorrow. Tomorrow we start at 9:00, right? 9 sharp, with the hands-on session on black hole Tom. Of course, you can take your time at your breakfast and the sea, but we invite you here. It's not obligatory, right? But yes, of course, that's a good point. Please bring your laptops here. So it will be a very hands-on session. You will be able to learn or relearn things you've been doing. So everyone is invited. And then we start with the coffee break. We start the regular session and talks. The same applies to people on Zoom. The hands-on session will be transmitted. It will not look great, I'm afraid, but we will try to do our best to transmit it online as well. I think that's it. Milena, anything else to announce?
Well, for those of you who want to join the radio telescope trip on Friday, I will give you more details tomorrow. So yeah, that will be the easiest because we have still some arrangements to confirm.
Trip to the radio observatory for people who are here. Okay, so I'll stop everything. Thank you for today and see you tomorrow.